Okay, we are recording. Hopefully it'll work. So the first thing I want to tell you is I have a handout here that I said was sort of new. It's not really new. I believe this handout was the first page or of the part 2 of chapter 4 packet. But some of you might not have gotten it because when I first uploaded it on Blackboard, it didn't have this front page. And I noticed that some people don't understand this, don't know what acids are, don't know what electrolytes are. If that's you, then you should read this again before the exam, because that's something you definitely need to know. I taught it in class, but it went by pretty fast, I guess. I also have the page here that I left out of the packet, which we did this activity last time, activity 1. So I'm giving you the solutions. I also have the review problems for exam 2, and exam 2 is again on Thursday of next week. And it's going to be on everything starting with limiting reactants, going through the end of chapter 4, and then all of chapter 5, which I'm going to finish today. Chapter 5 homework is up. It'll help you understand this. It's good problems. They're pretty much from scratch. I had to create a new assignment this year. And anyway, let's I also wanted to say we have this exam coming up. So I thought we could have a problem session or two, but they were so badly attended last time, and it basically was like 9 hours out of my life just waiting for people to come. Maybe it works better online. I don't know. What do you think? So we could do Zoom. I could do a Zoom over the weekend. I could do a Zoom Monday night.
Monday night.
Let's do Monday. Okay, what's a good time for you? Like starting what time? If I do it like an hour and a half Zoom, it's like 7, 7:30, 8. No, no, at night. Oh, night. So how about, is 7 okay, or 7:30? 7? Yeah, you can still come to my office hours. So, all right. So 7 is better than 7:30. Okay. All right. I could stay on as long as people are there. I'm not going to stay forever, but at least an hour and a half or so. And now what about another session? Should I do Tuesday after class? I could also do Tuesday after lab at 3. But I know there's another lab at 4. Or I could perhaps do a Tuesday night Zoom, or something. I mean, what do you think? All right, I'll do, but that's not good for people that have lab, right? So what are the people that have lab? It's at 12 to 3 and then 4 to 7. So people who have lab on Tuesday, what's good for you? Because I definitely could say Tuesday after class. That's not a problem. But I want to do another. How about I could do a Wednesday night Zoom. Who wants that? Raise your hand. You think that's just too late though, maybe? I don't know. Tuesday night Zoom? Okay. Okay, Tuesday at 7. Oh, that's Halloween. Well, you're already coming after class. That's good. That's already on there. So is a Wednesday night Zoom better? I have office hours from 2 to 4 on Wednesday. If you come then, I will be there. All right. I will still keep my office hours, but I don't want one of these. I've had so many of these things where 2 or 3 people come. It's just, it's great for those people, but you could just come to my office hours. Anyway, all right. What about Wednesday? In the evening. I forget it. That's it. That's all I'm going to do then. I'll see you on Tuesday, right? So we could always arrange something else. But this is as it stands now. Okay, I need to get started here. All right, so I talked about calorimetry a little bit last time. And this is the apparatus that you use, or that we use, doing it on a low budget. And this reaction is all about putting a piece of aluminum. So a piece of aluminum was placed into this flask, that has hydrochloric acid in it. And this reaction happens as written here. The reason for this weird fractional stoichiometric coefficient is because I want this to be for 1 mole of aluminum reacting. So I just balanced it so it comes out right. 3/2 of H2, 3/2 of 2 is just 3. So the 3 hydrogens here exactly balances the 3 hydrogens here. You see this a lot in thermochemistry when you have fractional stoichiometric coefficients. Don't let them bother you, try not to anyway. So this aluminum reacts. At the beginning of the reaction, you're down here, probably at room temperature, which is like 25. Well, here it's 25.02. That's where this reaction starts. But then this reaction releases heat, the temperature goes up, and at the end of the reaction, it's 30. Well, I guess I made it go up a little too far because it only goes up to 30.97 degrees C. Okay, so we have a temperature rise because the reaction's given off heat. And so now, because it's heated up the solution, we can figure out by how much this temperature change is, this delta T, which if you subtract here, it's 5.95 degrees C. That will lead us to the amount of heat that was released. And the way that we do that, the way that we relate the heat, this is the heat, Q, which is delta H if the reaction is at constant pressure, just say that. And that's equal to the mass. And we're talking about the mass of the solution here, which, since you put a little piece of aluminum in it, this mass is the mass of the HCl solution, that 100 milliliters, plus the mass of the aluminum, which is almost negligible. This here, CS, as I talked about last time, this is specific heat. This is of the solution, but we approximate. We say, oh, this is a dilute solution of HCl. By the way, I didn't give you an amount of HCl, which means that HCl there's enough of it there to react with all the aluminum. This aluminum reacts completely. So the specific heat of the solution, well, the solution is mostly water. So this is approximately the specific heat of water. And we know that number. It's a very big specific heat because water has lots of places to put energy. So it's 4.184 joules per gram degree C. We also use the fact that the density of water is 1 gram per milliliter. So when we calculate the mass of the HCl solution, we say that's approximately equal to the mass of the water, because it's a dilute solution. And the density is 1 gram per milliliter times 100 milliliters. So that's 100 grams. And then we add the 0.125 grams for the aluminum. And you can see that it's 100.1, but that's the last sig fig is the one I underlined. So the 0.125 is really not going to matter at all. So the Q is this mass, which is 100.1, let's do that, grams, 4.184 joules per gram degree C times the delta T, 5.95 degrees C. So this is MCS delta T. And when you multiply those things together, you get 2,490 joules. So that is the amount of heat that flowed from the reacting chemicals into the surrounding solvent, and now that heat is contained by the styrofoam cup. But as one of you noticed last time, there's a little bit of a problem with this. This mass, I already did this. This is the 100.1. delta T 5.95. Q is 2490 joules, okay? And now we have this reaction that releases heat, okay? We know it releases heat because the temperature went up. So the temperature went up. That means that the reaction is exothermic. Heat is released. Well, we also know that this is the Q, and that Q is the delta H, at least at constant pressure, which we just have to say to be technically correct, but we don't care much about in this course. The thing is, what does the sign of delta H have to be in a case like this? Delta H must be negative. Why? Because we went from here, the reactants, Al plus HCl, go downhill to H2 plus AlCl3. Wait, is that right? Yeah. Okay. And that means that heat is released. You could see that the final state, this is the enthalpy of the, this is the enthalpy diagram. Enthalpy of the final state where it ends up is lower than where it started, right? And we know that delta H is the final minus the initial, which if you're subtracting something larger from something smaller is going to be negative. So what we need to do is we have to change this equation a little bit, that this MS delta T equation, MCS delta T, is not quite right. And we actually have to make it Q is minus MCS delta T in order to make the sign be negative, because this is positive, this is positive, this is positive. Okay, now why would we have to do that? And the reason is because where are we measuring the temperature? We're measuring the temperature in the surroundings. You can't measure the temperature in the system. You can't stick a thermometer in the aluminum or inside. You can't do that. You can't measure that the heat is flowing out of that system. So you have to measure it in the surroundings. That's where we measure everything. So any heat that leaves the system is entering the surroundings. So there's an opposite sign there between the Q from the system's point of view and the surroundings point of view. For all you need to know, though, is that there's a negative sign there. Okay. And so when you do that and you use the above equation, instead of getting 2490, you get negative 2490. And now that's for reacting 0.125 grams of aluminum, but I want to know what is delta H per mole of aluminum. So I simply have to divide by the number of moles of aluminum, which is a simple conversion from grams to moles. 26.99 grams to 1 mole. And that comes out to 0.00463 moles of aluminum. So here's the delta H divided by the number of moles. And that comes out to negative 538 joules per 1 mole of aluminum. Okay, so that is the delta H per mole for that reaction. Okay, so that's all I'm going to teach you on calorimetry. There is a lab on calorimetry, and I think, I don't know, not next week. It's like in 2 weeks that you'll need to do some calorimetry measurement. I'm never going to ask you to solve a problem like this. It's just a little bit too involved. Okay. So I'm going to move on to talk about another property, very important property of enthalpy, which is going to sound a little out there, because I admit it, thermodynamics, which is what this really is, can be a little out there. And here it is, okay? I have to tell you something that's going to sound very weird. So here it is. Enthalpy and internal energy, the same thing is true for internal energy, are what we call state functions. And this is there's a lot to this concept, but in our, and at our level, what it means is pretty simple, okay? What it means is that H depends, I don't care about delta U, so I'm not going to even talk about it, but enthalpy depends only where the system is, where the reacting chemicals are right now, at this point in time. Take a snapshot. That the enthalpy is determined by what's going on right now, what the temperature is, what the chemical, are they solid, liquid, or gas? What is their state at the moment? So enthalpy depends on where the system is at right now. It doesn't matter how it got there. It doesn't matter. I'll give you an example. So for example, if I could write with this pen, the computer has to catch up. So if I have liquid water, say 1 mole of liquid water, and it's at 25 degrees C, the enthalpy is going to be a certain specific value that it will always be every time you have 1 mole of liquid water at 25 degrees C. And I'm going to say 1 atmosphere pressure. It's always going to be that. Doesn't matter if it started at ice at -10 degrees C, and that was melted, and then it was into liquid, and then it was heated to become 25 degrees C, or it started at steam at 200 degrees C that was cooled and then turned to liquid and continued to cool to 25 degrees C, okay? It doesn't matter how it got there. It will always have the same enthalpy. Now, that's very important. Maybe it doesn't seem so, but the reason that's important is because it leads to the fact that all paths that take a bunch of chemicals from point A to point B, all paths, no matter that path, this crazy path, all paths have the same change in enthalpy, because the first state, the initial state, it is what it is, depending on what the state is. The second state is what it is, depending on what the state is. So it's only the difference in these two values that matters, not the path. So I'm just going to write a silly little picture here to illustrate that. The delta, here's the delta H for going from reactants to products. And it doesn't matter if I go straight there, the easiest way, or if I take a very crazy path like that, or if I take another crazy path like this, okay? It doesn't matter. All the paths have the same delta H, and that is because delta H is the enthalpy of the products minus the enthalpy of the reactants. That's the final minus the initial. And because these guys are only depend on the current state, as long as that state is the same for final and initial, the change in enthalpy is the same. So this is very nice. It's a very nice thing that allows us to do all kinds of calculations of delta H. Okay, so let me show you what I mean by this. And I'm going to, first I'll give you something called Hess's law, which puts this into words. So here is Hess's law. And you don't even have to really understand what a state function is to understand Hess's law. If a reaction may be broken down into steps, any kind of steps that gets you from point to the reactions to the products, the delta H for the overall reaction is the sum of the delta H's for all of the steps. Okay, so here's a simple example. Okay, Suppose I know the delta H for this first reaction. Reactants form a different compound. Let's call that compound M, okay? And then I also know the delta H for M forming the products. So I have a delta H for this first reaction that is known. And I have a delta H for the second reaction that is known. So if I want to know what is the delta H for just going from reactants to products, I just add up these two equations. You can see the M's are going to cancel. I have reactants plus M goes to products plus M, and the M's cancel. This is just like a math equation. And you end up with reactants goes to products. And what is the delta H for this reaction now? It is the sum of these two. So you add two reactions, add their delta H's. So you could see how this could be very useful to figuring out delta H's for reactions when you don't know them. Okay, and let's do an example. This is chapter 5, yeah, sorry, a little fast maybe. Take them, just take them. These are old, but I don't know if you have. Do you have this packet? That's the important one. Okay, so let's go to this activity 3, number 1. And I would like to figure out what the delta H is for this reaction. And I can't seem to find it in a book or anything, but I found these two reactions in a book. The reaction of 4 NO2s to give 2 N2s, 4 O2s, and I have a delta H. And then this other reaction between N2 and O2 to give N2O5. So I noticed that, that if I add up these two reactions, let's see what happens. So if you add these two reactions up, I just add up everything on the left. Oh, what am I doing? Okay, so I just added everything up. I just took and added all this on the left, all this on the right, and I noticed that I could cancel some things. What can I cancel here? I could just cross those out, but I could do something else, right? If this was a math equation, maybe you'd subtract 4 O2s from both sides. And this would go away here. So you would end up with N2O5. And here you'd end up with 1 O2. Oops, I don't have N2 anymore. So this is just 4 NO2 plus 1 O2. And look, oh, wait. Oh, I think it's a typo in here. Oh, God. I think this should be 1 O2 here, right? Because it's 1, 2, 3, 4, 8, 5, 10. Yeah, this 5 should be a 1. Please change that. That's bad.
Yeah, that's
Oh, yours is right? So I used the right version for you, but I didn't for me. So, okay. So yours has the 102, I guess. All right, fine, great. So this is the reaction that I wanted. And no, this one's right here. So I have this is the sum. This one is the same as this one. This is the sum. Okay, the intermediate, the two equations I added, this is a 5. Yeah. It is on your paper, right?
Yeah.
Okay. So your paper was right. All right. But now, what is my enthalpy change for this reaction? It is simply negative 32.8 plus negative 86.2, which adds up to negative 119.0 kilojoules. So I have just figured out the delta H for this reaction here by finding two related reactions, adding them up, canceling things, and getting the equation that I want, and and adding up the two delta H's for the equation that ended up equaling it. Okay, so that's something we do. That's a type of problem, and that is a type 2 problem. Remember, I'm trying to tell you all the different types of enthalpy problems. So that's a type 2 problem. Now, it's not always like that. Sometimes you have to manipulate the equations before you add them. You have to maybe reverse one, or maybe you have to multiply everything through by a constant. But what happens if we multiply an equation? We multiply everything in that equation by 2. So we're talking about reacting twice as much material. What is going to happen to the delta H? It's going to what?
It's gonna be, also
Multiplied by 2. So when you manipulate thermochemical equations before you add them up to get the reaction you need, if you multiply through by a constant, you have to multiply the delta H by that constant. What about if you reverse an equation? What does that do to the delta H? Remember, if it releases heat going one way, it's got to absorb heat going the other way. You have this reactants and products. If this is going down, reactants to products, it releases heat. And if you make these the reactants and these the products, it's going to absorb heat. So when you reverse the reaction, you have to change the sign of the delta H. So you have to remember that. So sometimes equations must be manipulated before adding them. So if you multiply an equation by a constant, you must multiply delta H by that constant. Okay, if you reverse an equation, must change the sign of the enthalpy change. Okay, so let's do this problem here. This is activity 3, number 2. And we want to get the delta H for this reaction here. 2H2O2, it's hydrogen peroxide, goes to 2H2 plus O2. Okay? But we're given these two equations. Now, how on earth am I going to manipulate these equations to do this? And I'm going to give you something that you should always do. So what you should always do is look for the most complicated molecule in this equation. So what's the most complicated molecule in that equation? H2O2. Most complicated structure, the most atoms, yeah, I'm not talking about the coefficients. That's not relevant. So this is the most complicated molecule here. So what you need to do is look at the equations that you're given and figure out, what do I have to do to get the most complicated molecule on the correct side of the equation? And notice this is on the left side. Okay? Where is H2O2 in any of these equations? It's on the right. So what's the first thing I'm going to have to do? Can you say that again? Reverse it. So I need to reverse. I'm going to call this equation 1 and equation 2. Reverse equation 1 to get H2O2 on the left side, because over here it's on the left side. So I'm going to take equation 1 and reverse it. And so that means I'm going to have H2O2 here on the left. And of course, I have to change the sign. It's going to be plus 191.2. Because you reverse the equation, you change the sign. That goes together. All right, now are we all good on the H2O2? Look at the equation that we want. That's this one up here, the top one, right? How many H2O2s are there? So what do I have to do to get 2 H2O2s on the left? Multiply by 2. So now I'm going to multiply that by 2. 2 H2O2 goes to 2 H2. I think plus 2 O2. So now, what is the delta H for that reaction? What do I have to do to the delta H? I have to multiply it by 2. And 2 times 191.2 is 382. We're talking, this is still reaction 1. Okay, first I reversed it, then I multiplied it by 2. And so now for the new equation here in red, this is the delta H. All right, so now, okay, what's my second most complicated? H2O. Okay, now is H2O on the right side of the equation? It is. It's over here. Here's the H2O, and here's the H2O. But what do I have to do to the H2O? Yeah, you'll notice that the equation I want has a 2 H2O over here. And the equation I'm going to use, I'm going to have to multiply equation 2 by 2. So I'll get 2 H2. 1/2 times 2 is 1. Gives me 2 H2O. And my delta H for that is 2 times negative 285.8 kilojoules, or minus 571.6. Now I'm going to add these two. So when I add them, I get, okay, 2 H2O2 aqueous. You see, I have 2 H2s on both sides, right? I cancel them. Oh, what happened to that? And I have 1 O2 on this side I like to keep the arrows all lined up. That makes it less confusing. Okay, reactants, put an arrow, even if it's a big space, goes to 2O2 plus 2H2O. Okay, but you could see now that I have 1O2 on this side and 2 on this side. So I can get rid of it. Plus nothing. Okay, and that's the equation I want. There it is. And now I have to add up the delta H's. So I have 382.4 plus negative 571.6. And when you add that up, it's negative 189.2. So that's the delta H for this reaction here.
Does it matter when you're doing the sum, if you were to put 2H2O first instead of the gas?
She's asking me if it matters what order this is in. No, it doesn't matter at all. Doesn't matter what order you write reactants in or products in a chemical reaction. Okay, so that was a pretty complicated one, right? We had to reverse one equation, multiply by 2, and then we had to multiply the other equation by 2. And that's unusually difficult. I wanted to, students always say, oh, the teacher did the easy example in class. So I didn't want to be that teacher, but maybe I should have done an easier one. But here's an easier one. And I would like you to do this one. So here are the two equations. Okay, and this is what you want to get at the end. So figure out what is the most complicated chemical in this equation, and is it on the right side? Oh, this is activity. Oh, sorry. Yeah. This is activity 4. You're sighing to yourself. It's in here. Don't you have this one? You've come to class the last several classes.
No, I think I just.
I'll take it, but I hope. Does anyone have 2 of these? Because I really should have some extras, and I don't. I have only 1 left, and I print way more than I need. So if you have an extra, just in case somebody needs it. I don't need it now, but just work on the problem later. Look for it. So you should be noticing here that in the equation that you're trying to get the delta H for, the FeBr3 is on the right. So what are you going to do to one of these equations? What do you have to do? You have to get an FeBr3 on the right. How are you going to do that? Reverse what? Yes, you're going to reverse the second equation. And that will put the FeBr3 on the right. And what are you going to have to do to the delta H when you do that? Change the sign. And see if then that will add up with equation 1 to give you what you need here.
That also have to switch half BR2 to the left. Yeah.
You have to flip this entire thing. So yes, this will all be on the left and this will all be on the right. And you'll have to change the sign of the delta H and then take a look at equation 1 and see if you could just add it and you'll get the thing you need. So I was telling some people here, don't worry about the little molecules of PRs and everyone wants to worry about the free gas and all that. If you worry about the more complicated molecules, just all of them will take care of themselves. So it's not always as complicated. I mean, I'm going to hand it back. First, this is the reverse here. Yeah, the reverse, there's no change. Oh, okay. I don't know. Oh, well, the second one, it was on the 8th, but it was, right. I did this. Did you get negative 268? No. Why? You don't have to modify. You have the light and that you are free. One, two, then you know. But always. And you have one, you have this very smart. Yeah, so. All right, I'm gonna go over this briefly. I think you people have gotten the hang of this. So I'm going to reverse 2, because that's going to put the FeBr3 on the left, on the right. That's on the left is going to be on the right. So let's reverse it. FeBr2 plus 1/2 Br2 goes to FeBr3, and the delta H would be negative 18.4 kilojoules, okay? And now I'm going to leave one as is, unchanged. Fe solid plus Br2 goes to FeBr2. And here's a beautiful thing that happens. The delta H is the same. I haven't done anything to it. The beautiful thing is, if you worry about the larger compounds, wait, something I did wrong. Wait, hold on. No, if you worry about the FeBr3, for example, in this problem, everything else worked out. The FeBr2s cancel. Look, you have a 1 plus a half. That gives you a 3/2 Br2. And here you have your iron. Goes to FeBr3. And the delta H is just negative 18.4 plus a negative 249.8, which is negative 268.2. So that's the answer. I will admit that it takes a little practice to get good at these problems, which is why there are quite a few of them in the packet. Okay. In fact, I'm going to tell you. Let's do one more thing with this problem, though, because it says, what is the heat released when 25 grams of iron react with excess bromine to yield FeBr3? So this is a type 3 problem that we talked about last time. If we have 25 grams of iron and we want to know how much heat, we have to first, please be quiet, it's just rude, go from grams to moles. using the molar mass of iron. Okay, so I could do that arithmetic there, or I could just go on and do it later. And now I have this equation here. So how am I going to find the heat? I know my delta H is negative 268.2 kilojoules, and that is per 1 mole of iron. So my moles of iron will cancel. And what I end up is negative 120 kilojoules. Now, I said how much heat will be released. Well, the negative tells you that heat is released. And the 120 tells you how much. So you wouldn't say negative 120 kilojoules of heat is released. You would say 120 kilojoules is released. Or you would say that the delta H is negative 120 kilojoules. These two things go hand in hand because we said we use the word released here. That means that the delta H is negative.
So that's possible.
I would have said 120 kilojoules of heat is absorbed. Yeah. Or delta H is plus 120. Okay, now, here's another example. Oh, I want to tell you that, let's do this one. I'll give you a special problem. Wait. Oh, no, we're not going to do this. This is a special problem. This is a really hard one. This one is difficult. So don't do this one unless you really feel like you want to test yourself. There are other examples that are a little bit easier that you can do. Okay. And we'll do some more at the end if there's time. I'm hoping that we have time at the end. Uh-oh, what's going on here? No, that's my niece and nephew. And my son when he was little. Ah, what's that? So that special problem, activity 4, number 6. But it's hard. Don't do it I'll give you some other ones. All right, so I want to move on. And I want to talk about another important topic. So we know that delta H depends on the amount that is reacting. That's for sure. We know that especially with what we just did, because if you multiply an equation by 2, you have to multiply the delta H by 2. The delta H depends on how much is reacting, but it also depends on other things. And it also depends on the temperature at which the reaction is occurring. But you know what? In this class, we always use 25 degrees C. So you don't have to worry. It depends on the pressure, which we always use 1 atmosphere, which is why we can have our delta H equal Q, because the pressure is constant. Okay, it also depends on the purity of the chemicals that are reacting. Okay, and now in the book and in handouts that I've given out, you might have noticed that some of the delta H's have a little 0. Has anybody noticed that? Maybe not. But when you see a little 0 here on top of a delta H, it refers to a standard enthalpy change. And what it means is that it's under standard conditions. So standard conditions are very simple. And maybe you think they're so, you really don't even have to say it, because I've just told you we're always at 25 degrees C. Standard conditions are 25 degrees C, 1 atmosphere pressure, and everything is pure. If this is true, then I get to put a little 0 there. All right. So that's why you see that a lot. But there is one standard enthalpy change that is extremely important, I would say above all the others, and that is called a standard enthalpy of formation. And it has the symbol delta H, right? Because it's an enthalpy change. The F here is for formation, and the 0 is because it's standard. Okay. And an standard enthalpy of formation is the enthalpy change for forming 1 mole of a substance. So you're forming 1 mole of a substance under standard conditions, 25 degrees C, 1 atmosphere. And the substance is pure. Okay. From what? Forming them from the elements that make up the substance in their stable forms. So it means the enthalpy change for forming 1 mole of any substance, pure, under standard conditions, starting with the elements in their stable form. So for example, if I form a compound with nitrogen, let's suppose I form the compound NO2. To form 1 mole of NO2, what are the elements that make up NO2? Nitrogen and oxygen. What is the stable form of nitrogen? N2. What is the stable form of O2, of oxygen? Never mind. Okay, now here's the other thing. So the delta H, okay, wait. So to form 1 NO2, that's only 1 N. If I start with N2, half of that is an N. So I have to make it so that I get 1 mole of my substance, 1 mole of substance. So I have to change the coefficients here. I have to make what the coefficients, whatever they need to be to end up with a 1 over here. And the delta H for this reaction is delta HF0 of NO2 gas. All right, that's one example. Yeah. Where does the other nitrogen go? Well, let's think about it. You know, a mole of N2 is 28 grams. So if I have a half a mole, that's 14 grams. So where does the other N2 go? You just use half of it, half of the amount. All right. So this is written out, what I just illustrated to you in equation form. And that is, I gave you this, it's in the packet. The standard enthalpy of formation of any substance is the enthalpy change. Oh, 298 Kelvin is just 25 degrees C. And 1 atmosphere pressure for forming 1 mole of that pure substance from the elements that make it up, the elements that comprise it. So I'm going to show you here a table. It's a limited table. I took and picked out delta HF0, standard enthalpies of formation for a bunch of different substances. And I put them in this table. And I want to notice something about this table. What do you notice when you look at this table? What is the thing that strikes you first? Yeah. Yeah, what's all the zeros for? Why all the zeros? Okay, so let's look at remember what this delta HF0 corresponds to. It corresponds to forming 1 mole of a substance from the elements that make it up. What are all the zeros under? The zeros are next to N2 has a delta HF0 of 0. What does that mean? What reaction corresponds to the delta HF0 for N2. It means you're making 1 mole of N2, right? So this, if I want to know what reaction this corresponds to, I'm making 1 N2. And what am I making it from? The elements that make it up in their stable form. What's the stable form of nitrogen? It's, you're not, delta H is 0 for this reaction. So the delta HF0 of N2 is equal to 0, as it is for every element in its stable form. Because all of these zeros here correspond to making 1 mole of the element in their stable form from the element in its stable form. In other words, this corresponds to, for Cl2, this delta H is equal to 0, and it's the heat of formation of Cl2 gas. Okay, all of these reactions, O2. If you're pouring 1 mole of O2, it forms from O2. This delta H is 0 because nothing's happening. So delta HF0 of O2 gas is equal to 0. So that's what all the zeros are. They're all for elements that are already in their stable forms. Okay, let's look at a curious one though. What about diamond here? When you see equations in thermochemistry and there's solid carbon, you see it says carbon and in parentheses it says Gr. That does not mean gas, that means graphite. Graphite is the stable form of carbon. Diamond is not the most stable form. So what would the equation be to form diamond if we form carbon diamond from elements in its stable form? So we want to form 1 carbon diamond. What would be on this side? What's the stable form of carbon? Graphite. So you would have to go carbon graphite to carbon diamond, and the delta H for this reaction is 1.90 kilojoules. And this equation corresponds to forming a mole of diamond from 1 mole of carbon in its stable form, because carbon is the element in diamond. So this delta H is the delta HF0 of carbon diamond. Okay. So, okay. So let me take a few, like I'm going to look closely at this. So I'm actually going to rewrite that section of the table over here. Oh, yeah.
So it's just the state for this. It's not graphite diamond, is that?
It's the state that's different. The stable form of carbon is the state graphite, not the state diamond. Yeah. Okay, so let me look at these 3 entries here. I'm going to rewrite them. The substance, and here's the delta HF0 in kilojoules per mole. And we have oxygen. We have O2, and we have O3. Does anyone know what O3 is? Oh. What? Let me see if it's still recording. Yeah, it is. Share screen. Oh, it's not there. It's called ozone. O3 is ozone. Oh, what am I doing? I hit something wrong and it. Oh, where's the view? Great. Yeah, it is a layer in the atmosphere, exactly. Well, now I'm in a completely different window. How do I get out of this? Oh, I can't get rid of this. Oh, good. I didn't see the X. It was like it wasn't there. Okay. Oh, and I have to write those again now. Well, you might as well ask your question. For reactions, she's asking if the conditions for when a reaction has to happen regarding stability. And for spontaneity of reactions, that actually doesn't have to do with delta H as much as something called entropy, which is a topic in second semester. So reactions can happen that have positive or negative delta H's. They all can happen. All right, so we have these three numbers here, and I would like us to understand these numbers better. Don't forget what these numbers are. In fact, I'm going to write down what all the equations that these delta H's correspond to. So the first one corresponds to forming 1 mole of oxygen atoms from oxygen in its stable form. Now, what is the stable form of oxygen? It's O2. And you could tell that it's the stable form of oxygen is O2 because this is 0 here. Because forming O2 from its stable form, which is O2, has no enthalpy change, right? Now, is this equation correct for the equation representing forming 1 mole of oxygen atoms from an oxygen molecule? Is this equation balanced? No, I have to put a 1/2 over here if I want to have a 1 over here. And delta H for this reaction is the delta HF0 for oxygen atoms in the gas phase. And what is that value? It's plus 249.2. So what that tells you with this positive sign here is it tells you that going from O2 to O, well, I guess 1/2 O2 to 1 O is uphill. This is positive. It's endothermic. It tells you that oxygen atoms are less stable than oxygen molecules. Is that a surprise? What did we learn about last time? When you form bonds from atoms, you stabilize the situation. Here you're going from the bonded oxygen atoms to the unbonded oxygen atoms. So this should make sense, okay? Oxygen atoms are less stable than O2 molecules. That's why this is a positive number here. Okay, let's go to O3. To form 1 mole of O3, and I start with oxygen in its stable form, O2. How many O2s are going to give me 3 O's? This is the tricky thing. You have a 2 here. If you put a 3 halves times 2 is 3. So that's why I put a 3 halves over here. This equation, the delta H for this reaction is the delta HF0 for O3 gas. Okay. I'm sorry, I can't hear you. Speak up a little bit.
That's saying that
Yeah, this is all standard conditions. 25 degrees C, 1 atmosphere pressure, everything pure. So this is saying that if you go from O2 to O3, it's also uphill, and that delta H is plus 142.7. And that's what the delta HF0 for O3 gas is, plus 142.7, which is to say that ozone is less stable than oxygen. It's an uphill process to get from the element in its stable form to ozone.
Try to go back to the.
Yeah.
I think that's why.
Right. So going, it would that I just there may be an activation energy there. There may be you may have to have some other. I think it would be spontaneous, but because you also have 1.5 moles on. It's a long story. I don't really want to get into it, but it's not just enthalpy that determines the direction of a reaction. It's also the disorder of each side of the equation. O2 to O3 would never be downward. It's always O2 to O3 is always going to be upward. You can't change that.
Oh, I'm sorry, it meant O3 to O2.
That would be downward. Yeah, that would be downward. All right, I need to move on, all right? Because I'm not going to get to what I need to. All right, so I want to talk about a couple of other entries in that table. If you see sodium chloride, what's the number for the delta HF0 of NaCl? Notice that number is quite negative. So that means that if you're forming 1 mole of NaCl and it was solid, from the elements that make it up. Now, what are the elements that make up NaCl in their stable form? Cl2 and sodium, just plain old Na. So it'd be one of those, and there'd be 1/2 of these. Okay, so this is very downhill. Here's your elements. Here's your solid NaCl. And so this is exothermic, forming NaCl from the elements, releases energy. So delta H for this is delta HF0 for NaCl. Now, why do you think that would be negative? What's going on in an NaCl crystal? Which is what this is. You have Cls, you have these positive and negative charges here that attract each other. Those are called ionic bonds. When you go in this direction, you're forming a lot of ionic bonds. And ionic bonds, bonding stabilizes systems. So you're forming lots of ionic bonds. That stabilizes the situation. Okay. I have another crazy example here. Where is it? Here it is. I'm going to just move this a little. This is nitroglycerin. And I put that on the chart because it's very unstable. Notice it has a very large positive. I don't know why this isn't, whatever. What's the number for nitroglycerin? Yeah, the delta HF0 for Ng is plus 381 kilojoules. Okay. So that means that if you start with the elements, and what are the elements? You've got nitrogen and oxygen, right? And there's also hydrogens in there that you can't see from that structure. And there's also carbon. These are all gas, graphite. It's an uphill battle to get to nitroglycerin. Now, does that make sense? What do you know about nitroglycerin? It's an explosive, right? It's very unstable. And here is your evidence. Forming nitroglycerin from the elements all right, is an uphill process. This delta H is the delta HF0 for nitroglycerin, and it is positive because this is unstable and the elements are more stable. And you will find this is true of a lot of explosives. They have positive delta H's of formation. Yeah. The less stable it is compared to the elements that make it up. Okay, now why am I telling you all this about delta HF zeros? It's because they are really extremely, extremely important. They're extremely important because they allow us to figure out delta H's for just about any reaction out there. And how do you do that? I'm going to show you. We use Hess's law. So we can use delta HF zeros to calculate delta H's of many, many reactions. And this is how you do it, okay? And we're going to use Hess's law, which, if you remember, for a reaction that you could break into steps, if you can break a reaction into steps, delta H for the overall reaction is the sum of the delta H's for the steps. Now, how is this going to help us? I'm going to show you a simple reaction, and I'm going to use it as an example, and then I'll tell you how you can extend that to many, many reactions. Okay, so let's suppose we have the N2O4 NO2 reaction. We've seen this reaction before, and I want to get the delta H for this reaction. How am I going to do it? If my pen works, I can do it. So the way to do it is to take, remember, you could take any path at all. And also that you don't actually have to do it in the lab. You can just do it on paper. So you could take any path at all that gets you from the reactants to the products. Well, I am going to take a very strange path. And this path goes through elements in their stable forms. So what are the elements in N2O4? There's nitrogen and oxygen. These are the elements in their stable form. It's not balanced. I would have to have one of these and two of these. Okay. So how is what I know about delta HF zeros now going to help me elucidate what the delta H is for each step, right? Because that's what I want. I want delta H for step 1 and delta H for step 2, because if I add them, right, then my path is going from here to here. So my delta H is going to be the sum of the delta H's for those 2 steps. Now let's look at this one, this step right here. That's taking N2O4 and forming the elements in their stable form from N2O4. Now, think about it. What is the reverse of that reaction? The reverse of that first step. It's taking the elements in their stable form and forming 1 mole of N2O4. What is that called? That is the delta HF0 of N2O4, right? Because you start with the elements in their stable form. The reverse of step 1 is starting with the elements N2 and O2 in their stable form and forming 1 mole of N2O4. That's the reverse of the delta HF0 of N2O4. That's the delta H for step 1. Okay? Do you understand that? Does it make sense? We have the elements here in their stable form, forming N2O4. The reverse reaction is delta HF0. So that means that this purple direction is the negative of delta HF0 for N2O4. All right, what is this arrow here now? It's forming 2 moles of NO2 from the elements that make it up. That step has a delta H that's twice the delta HF0 of NO2. So I should say here, this is for step 1 in the forward direction. Okay, so step 2 has a delta H equal to twice the delta HF0 of NO2. So that means that if I add these 2 things up, we're going to add up the delta H's for the 2 steps. If I do that, I get that the delta H for the overall reaction is equal to 2 delta HF0 of NO2 minus delta HF0 of N2O4. And if we look at the reaction, this was the reaction, was 1 N2O4 goes to 2 NO2. This was the original reaction, all right? So if you look at this original reaction and you look at this guy, you see that it is twice the delta HF0 of the product. So this is the stoichiometric coefficient of the product, right? The 2 here times the delta HF0 of the product minus this 1 is the stoichiometric. So minus 1 times delta HF0 of the reactant. This 1 is the stoichiometric coefficient of the reactant times the delta HF0 of the reactant. And if I write any reaction at all, I can generalize this so that the delta H of the reaction, delta H for any reaction, is the sum of the stoichiometric coefficients of each product times the delta HF0 for that product minus the sum of the stoichiometric. This sounds terrible, I know, but it's a lot easier to do, of each reactant times the delta HF0 of the reactant, of each reactant. I know that's a mouthful, but you know what? We're going to use it to do an example. It's a lot easier to use than to think about it generally. So here's a reaction. This reaction is in a handout. Here it is. It's the same handout that has the delta HF0s on top. I picked a reaction with lots of great stoichiometric coefficients. Okay. And so what is the delta H0 for this reaction? So I'm going to use this equation, which I kind of write in shorthand here. The sum of, take the stoichiometric coefficients of each of the products and multiply by the delta HF0 for each of those products. So let's do it here in this particular case. Okay, let's start with this 4 here. That's the stoichiometric coefficient of the first product times, I would have to multiply by the delta HF0 of that first product. But it's a sum, because in the example, I didn't have to worry about a sum. I only had one of each. But now I have to add to that the stoichiometric coefficient of my second product times the delta HF0 of that product, which is water. So that's the sum of the stoichiometric coefficients of each product times its particular delta HF0. And then I subtract, and now I have a 2 here, 2, that's the stoichiometric coefficient of the first reactant times the delta HF0 of that reactant, plus stoichiometric coefficient of the second reactant times the delta HF0 of that reactant. So what I do is I tend to distribute this negative sign immediately so that I don't forget to do it because it's bad if you forget to do it. So I would write this as 4 delta HF0 of CO2 plus 6 delta HF0 of water minus 2 delta HF0 of C2H6 minus 7. See how I distribute the negative sign? So that's the first thing. Now I can simplify this right away a little bit. If you look at the chart, you'll notice that one of the numbers is missing. Which number is missing? And why would I not have the delta HF0 of O2 in this chart? It's 0. So if I were to put O2 here, it would be 0. So I just don't include it. You're supposed to know that that's 0. So I don't have to worry about that term. But I have to worry about the others, okay? So I would have 4, and then I look up the CO2, minus 393.5 plus 6 minus 285.8 minus 2 times minus 84.68 kilojoules. And what you need to be careful of is these signs. So when you subtract a negative, you get a positive. So you have to be careful about that. So this adds up to negative 3,119.4 kilojoules. And that is the delta H for the reaction that we're trying to find, this one. And that's how you use delta HF0s to do that, okay? So let's do this example. Activity 4, number 7. Activity 4, number 2, I'm going to make that another special problem to do at home. But this one we do right now. We still have 15 minutes, I think. Yeah. So you might want to put 1s here. And what you're going to use is that delta H for this reaction is the sum of the stoichiometric coefficients of the products times the delta HF0s of the products. I'm going to abbreviate it. Not very legible. Minus the sum of the stoichiometric coefficients of the reactants times the delta HF zeros of the reactants. And here's the delta HF zeros that you need. Just try it. You want me to start it with you? All right, we got coefficients here of the products. It's always products minus reactants. So we have 2 times the delta HF zero of water in the gas phase. And what do I have to add to that? Here's another one, another product. Plus 1 times the delta HF zero of N2O. Right, I'm adding up all the coefficients multiplied by each delta HF zero. For the products, yes. It's because of this, what we're using to do here. We're basically taking a root that forms the elements from the reactants, so that this direction here of this first thing is the negative of the delta HF zero for the reactants, because we're going in the opposite direction of forming. And then this direction is forming the products from the elements. So these are positive delta HF zeros. These are negative delta HF zeros. No, we're not going back. Well, I guess you consider that backwards of the heat of formation, backwards of the enthalpy of, yeah. The first step is backwards. That's why we have the negative sign in front of the reactants. And that's what we have to do next. We have to subtract 1 times the delta HF zero of NH4NO3 solid. Can't erase it. There. There are plenty of examples to go over this. Activity 4, number 2 is another one. You have to do this a few times. You have to force yourself. This is the other one, number 2. If you want to work on this one, there's all some good coefficients here. You want to find the delta H zero. Did anybody add this up? He's right. Whoever said that. Who said that? Might want to look at this one next. Try to see if you can actually work this out. This is a special problem. You can start it now. Start with the coefficients of the products times their corresponding delta HF0. Right? And then subtract it for the reactants. Then distribute the negative sign. Except here, what's this equal to? The goose egg. Yeah. It's just practice. What about this number 3 here on activity? What are we up to? Whatever activity this is. 4, yeah. Write the reaction corresponding to the heat of formation of solid sodium oxalate, which I give you the formula. So the reaction whose delta H is the delta HF0 for this. What would I have to start with? Elements. The elements in their stable form. So sodium, carbon, graphite, and O2. But I have to get the coefficients right. All right, I'm done today. That's enough. Study, everybody, study.